Alright guys, if you haven't seen my last video where I go over this equation sheet, take a look at it right over here. In this video, I'm going to go over some of the equations that I kind of was unsure about. But just to summarize, we had kind of a run through of each equation. All the constants I wrote in green, atomic physics related stuff I circled in pink, quantum mechanics in red, relativity in blue. So you can see a lot of stuff in this first column right here. Actually, let me pull up this little hand. I also got these little notes right here, which are useful. We're going to go through those in a second. But you can see right here we got some green. All this stuff is green. Everything circled in green is a constant. So you can kind of just, I don't know, research that if you want, but not too important. The most important stuff is the equations. Then we got here 1, 2, 3, 4, 5, 6, 7 blue equations. And this one here I circled blue. I know it's kind of hard to see. If you want to see more high quality, check out the previous video where I kind of go over each of these equations in depth. Right now, we're just kind of looking at it broad. And this equation here is lambda times frequency equals c, the speed of light. So I circled this in blue, but really this equation is kind of general. It appears everywhere. So that is relativity. Then we got red, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I think 9 equations from the quantum chapter. And then we got pink equations here, 1, 2, 3, 4, 5, 6, 7 equations in pink. 7 equations, general relativity. 7 equations, atomic physics. About 9 or so equations, quantum mechanics. So you want to break shit down like this and kind of chunk stuff into your mind. So last video, we went over a lot of these. I'm fairly comfortable with some of these equations, so I'm not going to go over all of them. But I'm just showing you this as a proof of concept or idea of what you can do to study. So sit down and try to go through this on your own and ask yourself, where are you confused? So right here, the notes that I wrote are things I don't know. And you can see I've broken stuff down into this section here, this section here, this section here, and then I got a little lazy with this section here. I've broken stuff down into, over here we got 2 constants that I don't really know. This constant right here, r subscript h, I don't know what this is, so I'm going to try to find it in the book. And then another constant all the way down here, a subscript 0 is equal to 0.052 nanometers. I got this section here, which, take a look, it is this equation right here. Q is equal to, inside the brackets, we have capital M subscript x. By the way, I made a mistake here. These should be minus signs. Capital M subscript x minus capital M subscript y minus capital M subscript alpha. I don't have little alpha symbols, so I just wrote alpha. All of that is being multiplied by this 931.5. And they also tell you the units, mega electron volts per U. And this U is actually a unit of mass, the atomic unit of mass, which is given to you right over here in this green. So you can convert between U and kilograms if you wish. Interestingly enough, there's another equation that looks very similar, which is right over here. And I chunked these two together because they look identical. Why do they look identical? Well, they both have this 931.5. They both have units of mega electron volts. And they both have 3 things over here inside the brackets, which are being added or subtracted together. So these I put in the same kind of section here. I don't know either of these, so we're going to take a look at them. And I think these are atomic physics related equations. So we have constants, atomic physics related equations. And then here we have special relativity. So overall, special relativity, the Lorentz transformation equations are super important. We're going to take a look at those because I'm going to start this entire video by looking at the special relativity equations. We have gamma over here, and then we have 1, 2, 3, 4, 5 equations that I don't know. And these are the equations here. So I'm literally just going to tell you what they are because I have read a little bit, but we'll pull up the book and take a look together as well. We got relativistic momentum, which is P, relativistic kinetic energy, which is K, relativistic energy, which is E, and then kind of an equation here that is very similar to the Lorentz transformation equation, except it's a Lorentz velocity transformation equation. This little U right here is velocity. This little prime is velocity of the moving reference frame. This little U is velocity of the non-moving reference frame. And there's a bunch of shit going on in here. So we got three things over here: momentum, kinetic energy, energy. Here we have velocity. And then here we have another kind of famous equation Einstein talked about, also relativistic energy. You could use this equation to derive this PEK. Basically, it says energy squared is equal to P, which is momentum squared, times C, which is speed of light, which is actually given to you right over here. That is a constant. Speed of light squared plus mc squared, and that entire thing is squared over here. You'll see this mc squared appears quite often. We have an mc squared right here in the relativistic energy. We have an mc squared right here in the kinetic energy. Actually, there's another mc squared right here in the kinetic energy. And then we have an mu in the momentum. Cool. And then I have here, I kind of started writing stuff about quantum mechanics, which I was unsure about, but I got a little lazy. I don't want to type out all this stuff. Like, this equation here is difficult to type out on this little notepad, so I'm just going to talk about this with words. But you guys have to do this as well. Look at this equation sheet, ask yourself, what do you know, don't know? Sit down with a piece of paper or text, write down what you don't know, and then go through it one by one. Or if you write it in text like this, you can plug this into ChatGPT and be like, hey, what does this equation mean? I have to study for an exam, please help me. In this video, we're going to go through the textbook, which I have here. Take a look at all these sections, relativity, all the sections that I went through. You can check out all the 7-minute summaries of those if you wish. But right now, I've just skipped to the summary section of relativity to see what we can find here. Off the bat, this first box over here is talking about linear momentum, the relativistic expression for linear momentum. So let me zoom in here a little bit. You can see P, it is bold with a little vector quantity over here because it is a vector, momentum is a vector. Then you can see one way of writing it over here. And if you've seen this term over here quite often, you can rewrite this as gamma. 1 divided by this thing in the square root gives you gamma. So this thing here, gamma times mass times velocity. Velocity, they use a letter U over here, right? This is velocity. That gives you relativistic momentum. Momentum in classical mechanics is mass times velocity. In relativity, you have to multiply by this gamma term because if you go really fast, the momentum changes. You don't want to break speed of light and stuff like that. So relativistic momentum. So that covers our equation over here, right? And you could take a look at this, and since they include it here, 39.19, check this chapter, go to section 39.19, somewhere over here, relativistic linear momentum, boom. Actually, we can actually peep this really quick. Relativistic linear momentum, they introduce it here, they talk about how they introduce it. They talk about force, and then they give you a linear momentum problem right here. Let's take a look at that. Very interesting. Now we can move on. This equation is also interesting, but it's not in the equation sheet. Relativistic force. This is literally Newton's second law. Take a derivative of momentum, you get F equals ma. Not in the equation sheet, so we're not going to focus on it too much. We're going to move through. This stuff is super important to take a look at, but I won't spend too much time here. I just want to look at the equation sheet stuff. Kinetic energy. Here it is, the exact same thing. Kinetic energy, they give you a bunch of ways of writing it. And here, this equation is exactly the same thing as the one in the equation sheet. You just take this mc squared and you multiply it by this 1 and you multiply it by this gamma. You just distribute this inside. You can see the equation pops up right over here. So how I've heard about this a bit is this little 1 times mc squared is the rest energy, and the gamma times the mc squared is the relativistic energy. So you take the difference of the relativistic energy with the rest energy, and you get the kinetic energy, the relativistic kinetic energy. Right? They actually talk about it right over here. The constant term mc squared in equation 39.23, this one right here, is called the rest energy, E subscript r, of the particle. E subscript r is equal to mc squared. Go back to the equation sheet. You can see actually they give this to you right here. Relativistic energy, I wrote an I don't know. Now you can see, let me actually zoom in here. E gamma mc. Sorry, this is not the relativistic energy. This is not the rest energy. This is the one with the gamma in front of it. So you have to know that this is the total relativistic energy here, and then this little term mc squared is just the rest energy. And you can see that in the problem here. And you can also pull up this equation in the chapter, relativistic energy right here. Look in, they show you how to derive it, not too important, they show you the equation right here. Some more equations right here, they show you some cool graphs. And then boom, the energy of a speedy proton, an example that you can do. Cool. Let's see if there's another equation that looks familiar here. So this one here, relativistic linear momentum of a particle is related to total energy through the equation. Boom. And then they give you 39.27. You can again check where this equation pops up and see if there's an example related to it. So this is also an equation which you see right over here. Energy, relativistic energy equation. And that covers all of the equations in relativity except for this one here, the Lorentz velocity transformation equation, which is actually this equation here. The relativistic form of the Lorentz velocity transformation equation is this. It looks pretty crazy, but they tell you u prime is the x component of the velocity of an object as measured in the s prime frame, and ux is its component as measured in the s frame. What does this mean? Check out equation 39.16. You can go over here, Lorentz transformation equations, Lorentz velocity transformation equations. Pull up this section, right? They talk about it, introduce it over here. Boom, they derive the equation after a few equations. No need to look at this, but if you do look at this and you kind of understand it, you're kind of on a good path because you know where it's coming from. You can kind of understand the equation a bit more from its foundations. So you can go down and read some pitfall preventions here if you wish. And boom, we have a problem, an example that you should do. This is a very interesting problem. It uses the equation here to get the answer of the problem. Another very, very good problem is this one here. This is a challenging one. You could try it out. It uses the equation, but there's a little trick there. So anyway, that covers all of the relativity-related equations. Again, I didn't go over like any problem specifically. I kind of just want to show you guys where is the equation, where is it coming from, and then you can kind of, at least if you know its name, check ChatGPT. It's on your phone. Literally just text it like a friend. Hey, I'm studying about special relativity. I want to learn about the Lorentz velocity transformation equation. Show me a problem. Talk about it to me. Please help me. Do this for all of these relativity equations, and then you're done with relativity. You can move on to the next section, which is, let's go through these equations here. Where did these equations come from? There's a Q, there's a 931, there's an EB, 931.5. Let's pull it up here. And actually, I'm just going to go through these chapters specifically looking at the equations here, just to remind myself what is each chapter talking about. So this is chapter 40, Introduction to Quantum Mechanics, sorry, Quantum Physics. We got the photoelectric effect. We got the Compton effect, which is actually another equation here that I marked as I don't know. That is this equation right here. I don't know this one. I haven't done a problem related to it, but now I know it's in this chapter 40. We got the de Broglie wavelength, which I also marked over here. That is this equation right here. I haven't done any problem related to it, but I know that it's in this section. Then we have the Heisenberg uncertainty principles, which are both here given to you in the equation sheet. Here is the energy uncertainty equation and the position momentum uncertainty equation. So these two, very interesting. I can't see anything else that jumps out at me. This equation here, E equals HF, also looks fairly important. And to be honest with you, I haven't seen this equation over here. So this is something that I would kind of mark. This over here, this equation specifically, 40.5, doesn't appear in the equation sheet, but it's very important. You could see E is equal to HF. Right here, you could see HF appears in the photoelectric effect. So this equation somehow uses this equation in it. And if you don't know how they're used and you don't know about this equation and you can't remember like in a question where this is coming from, and you don't have it in the equation sheet, you're a bit screwed. So take a note of equations that don't appear in the equation sheet while you're studying. But that being said, I do want to find this Q and this E equations with the 931. So I'm just going to keep going, but I'm going to go through it chronologically. Take a look at quantum mechanics. I'm just checking the summary, even though I don't think it's in this quantum mechanics chapter. Let me zoom in a little bit. So just quick little gander. Doesn't look like this is the chapter that I'm looking for. Let's go to atomic physics. Summary. Close this down. Zoom in a little bit. So we got boom, and actually this right here, RH, is the Rydberg constant, which is something that I wrote over here, R subscript H. So this constant is appearing in the atomic physics section. This is a constant that I found over here in the equation sheet. I didn't know what it was, but now we can see R subscript H, and we can actually confirm what the value is. So I'm gonna just pull up here. Actually, let's just sweep through the chapter backwards like this to see if we can find the Rydberg constant. Here it is. This equation, which is actually another one that I wanted to go through in the equation sheet. You can see that this one, F, is equal to KE squared over all this stuff right here. Forget about this thing kind of in the middle. Just look at this F and all of this stuff with the N subscript F squared, N subscript I squared. This equation appears right over here. This one right here. And I wrote this as I don't know, and I actually circled this as the atomic section. So this appears here, and I didn't want to write this down because it was too difficult to write these equations, but take a look at this little n squared here, n squared. This appears everywhere. And also take a look at this ke squared 2a0. This constant right here without the little h. You see how there's an h there? Remove this h, and this constant ke, which is Coulomb's constant, which is actually given to you right here. This is Coulomb's constant. Then you're being multiplied here by E squared, which is the charge of the electron. Electron charge is also given to you. It's right over here with the units. Units are very important. And then here you have 2a subscript 0. A subscript 0 is this constant right here, which I didn't know what it was about. But you could see this entire constant right here without the h appears in many equations. It appears right here in this frequency equation. This is frequency of a electron as it transitions from the n final to the n initial state. And I drew some little energy levels here, which is what I kind of thought about when I saw this equation. This constant appears here. Forget about the h. Why I'm saying forget about the h is because if you remove the h, this constant out front looks exactly the same as this constant out front. You got Coulomb's constant, K subscript E, electron charge squared divided by 2a0. And the a subscript 0 is right here. They also give you the units. So all of this stuff here in front, they give you the units. Same thing here. And there's another equation actually right here where they give you the same thing. You see how there's brackets here, Ke Coulomb's constant, electron charge squared, 2a subscript 0. And they tell you z squared over 2n right here. This whole thing actually, this entire thing right here, they solve it for you and they tell you it equals 13.6 electron volts. You see how there's a z right here and there's a z squared right here, n squared right here, n squared right here. Otherwise, everything else in the equation is the same. They just replace everything here in brackets as this 13.6 electron volts. Same thing here and same thing here, except here there's a little h. Why is there an h? Notice that the equations without the h, this one is energy. Energy, and they give you this. This one is also energy. Energy, and they give you this. So if you have energy divided by h, you get frequency, which is actually the equation that I showed you in the beginning, the E equals hf. Let me see. This right here, hf. So energy is equal to Planck's constant times frequency. But if you do energy divided by Planck's constant, you get frequency. So this equation gives you the frequency of an electron transitioning from the final state to the initial state. By the way, these are like energy orbitals of a atom. In this equation, it's pretty much almost the identical one, except they give you energy of an electron in this specific orbital. So you could plug in n equals 1, you plug in, solve for all of this. You have all of these constants given to you in the equation sheet. You just plug in n equals 1, n equals 2, n equals 3, whatever energy level you want to find, and you get the energy of the electron in that specific range. This equation here, same exact thing, except you have a z, which depends on the atom that you're talking about. So each atom has a different z number. I think hydrogen is equal to 1, tungsten is equal to 74. You can find any kind of z for any kind of element on the periodic table. You plug the numbers in here, all of these constants you have, they actually give you another way of writing it because there's an equal sign right here. So you just plug in 1, 2, 3, whatever energy level you want, This equation spits out the energy of the electron at this specific energy level. Same thing with this equation, but this equation, since you're dividing by Planck's constant, you're taking the energy and you're converting it to frequency. Planck's constant, by the way, is given to you right over here. Planck's constant has units of joules per second, and frequency has units of per second. So you divide by that, units cancel, and you get energy or frequency. So this equation here, this equation right here, and this equation right here are all very linked. I didn't plan to go through it like this, but since we saw it in the book right here, this equation, I wanted to talk about it anyway. And this nicely leads us into what is the Rydberg constant. So you see how here frequency, they manipulate this equation and they show you frequency divided by C is equal to 1 over lambda. So here they have the frequency of an electron transitioning from this final state to this initial state. Here they have the wavelength of the electron transitioning from this initial state to the final state, or from the final state to the initial state. And all you have to do is use this C is equal to F lambda equation, which is also given to you right here. So if you're being asked for the frequency of an electron moving from certain energy levels, you can use this equation. If you're being asked for the energy, you can use this equation right here. Or take a look at this. Since here there's no n final, n initial, there's just one n. This is the energy at that specific energy state. Here it is a transition. If the electron falls from the initial state to the final state, it spits out this kind of frequency. But you can also use this equation here to find the wavelength of this. And then you can multiply this whole thing by h, so you have hf. And remember, hf from this equation over here gives you the energy. I hope this is making sense. Anyway, this is what they do in this section over here. And then they further manipulate it. You could see they take this entire constant right here out front and they call it the Rydberg constant. And they tell you, provided the constant Ke, Coulomb's constant, E squared, charge of the electron squared, divided by 2 A naught, I don't know what A naught is yet, but it's in the equation sheet, times H times C, all of this stuff is given to you in the equation sheet, is equal to the experimentally determined Rydberg constant. And they don't give us a number, but I did see down here, you can actually do an example in this book. Here's the Rydberg constant. Let's see if they actually use it. 1 over lambda equals Rydberg constant 3 times, and here is the Rydberg constant, 1.097 times 10 to the 7 meters to the minus 1. Let's just validate if that's it. 1.097 times 10 to the 7 times 10 to the 7, and the units are meters to the minus 1. So now I can circle this entire Rydberg constant in green because I've seen it before. I feel fairly confident. And I've also seen this frequency equation. So I can circle this like, well, I can erase this little I don't know. And this equation is very similar to this equation. The reason I say they're similar is because the form looks very similar. They have an n squared over here. They have this constant here out in the front. You can plug in values of n. And then same thing for this equation down here. So I hope that was helpful and not too confusing. But if it was confusing, please take a look at the examples. Just do an example or two. You should feel fairly confident. If you don't understand the example, go back to where they introduced the equation. Read a little bit about it. Here's the transition states. You remember talking about these Lyman Balmer Paschen series. Take a look at my 7-minute summaries. I go through this very quickly. And try to kind of fit this in your head in a specific way. The way I like to do it is look at similarities between the equations. So anyway, that covers that. Let's zoom out and see kind of what I did here. So I still haven't gotten to this equation, and that's kind of my goal. But along the path, I found out what the Rydberg constant was. I saw that this A0 appears in multiple equations. It appears here, it appears here, it appears here. All these equations have an n squared. Here there's actually n initial, n final. Here there's an n squared. Here there's an n squared, and they all have this constant here, which is kind of closely similar to the Rydberg constant. It's not exactly the Rydberg constant, because remember the Rydberg constant had an hc over here in the denominator. But if you ever need the Rydberg constant, it's right here. Anyway, I haven't seen an equation that actually uses the Rydberg constant in this thing here, so it's good to know where it comes from. And where it comes from is, you take this equation, manipulate it a little bit, and you get this kind of simplified equation, which does the same thing as this one, finds the frequency of a transitioning electron from some energy state. For example, this one moves from 5 all the way to 1. It releases a certain amount of energy. Here's the energy. And then this 13.6 is important. 13.6, everything here is in units of electron volts. So I know that's a bunch of yapping, but I'm just trying to take a look at the equation sheet overall. A bit of like back of the napkin studying over here. So we covered that, some atomic physics sections. Of course, we are in the atomic physics chapter. But let me move back here to the summary and take a look at if I missed anything. So I was kind of taking on a bit of a segue, looking at this, Balmer series, whatever. You can read this if you're interested. The Rydberg constant, we kind of found out what that was. And boom, here are all the equations that I was talking about. So you can see this one over here, very similar to this one over here, except here we have a 2 squared, and here we have an n, you subtract by 1 over n squared. Over here, there's no subtraction in these big brackets, it's just n squared. Here, we have 1 over lambda, which is on the left side of the equal sign. So this entire thing gives you the wavelength of an electron transitioning from this series, transitioning from the third excited state, which you plug in over here, to the second excited state. And it releases some kind of frequency or energy or wavelength. Here, we have the energy of, we could read about it, the Bohr model of the atom is successful in describing some details of the spectra of atomic hydrogen and hydrogen-like atoms. One basic assumption of the model is that electron can exist only in discrete orbitals. Okay, whatever. I'm not going to read through this, but an important equation. And quantum numbers, so these little n's are quantum numbers, because, like they just said, the electron can only exist in specific energy states. So you plug in 1, you get a certain energy. You plug in 2, you get another energy. You can't plug in 1.5, 1.2, 1.3. It doesn't work like that. Quantum mechanics is quantum stuck in its ways. Here we actually have that A naught, which they call the Bohr radius. And it is a constant. You Google search what is the Bohr radius, ask ChatGPT what is this, but they give it to you in the equation sheet, so no need to stress about it. You just plug it in here, solve for an energy if you want to. Cool. And then further down, they tell you the frequency of the photon is, and they give you almost the exact same equation as before. You see there's an H over here. Here there's no H. Actually, inside the brackets, it looks a little bit different because it is an energy transition. This equation just gives you the energy at some specific orbital, n equals 1, 2, 3, 4. Here, they're finding the frequency of a photon emitted if the electron transitions from this n initial state to this n final state. It's very similar to this equation here, except here they're locking down the final state as the n equals 2 orbital. That's why they call it the Balmer series. Take a look at those graphs we saw before. Here, it's a little bit more open. You can choose any n you want here and any n you want here. You just need to have the n initial being higher than the n final. Or you can inverse them and it tells you the amount of energy you need to put into the electron for it to transition from a lower energy state to a higher energy state. Anyway, you can read up on this, but there's another very similar looking equation right here. Take a look at this. Almost identical equation. Let's actually put both of them into view here. They're literally identical. This equation here and this equation here, there's no difference about it. And here is where they pull out this 13.6 electron volts. So they take this whole thing, they solve for it, right? This minus sign here stays, there's a minus sign here. This n squared stays, there's an n squared right here. So they just take everything here in the brackets, they solve it, and they see that it equals 13.6 electron volts. Take a look at those graphs where they talk about the Balmer series and try to figure out what this 13.6 electron volts is. Or again, plug it into ChatGPT. I'm learning atomic physics. What does 13.6 electron volts mean? What is the significance? And then here they talk about quantum numbers. So this n is a quantum number. It can only be a certain integer. It cannot be 0, it cannot be negative, it can only be the positive integers. There are actually other quantum numbers which they introduce here. L, orbital quantum number, orbital magnetic quantum number, and they give you them here. I haven't seen this in the equation sheet, so I don't know if it's too useful, but you can read it if you wish. And then here they actually give you more atomic numbers. Spin atomic number, spin quantum number, spin magnetic quantum number. So there's quite a lot of quantum numbers. I'm not sure if you have to know those. And we have even more quantum numbers. These are the orbital angular momentum quantum numbers. You could see these guys can actually be 0 and all the integers. This one over here, the orbital magnetic quantum number, can actually be negative values. If L is 1, then the magnetic quantum number can be -1, 0, or 1. I don't know if this is too important. You can take a look at this if you wish, but it is not in the equation sheet, so we're going to keep zooming through. So that is this chapter, Atomic Physics. I haven't found anything that kind of relates to anything that I saw here, so I'm just going to keep zooming forward with chapter 43, the molecules and solids. Let's check the summary again. Zoom in here to see what's going on. So we got ionic bonds, covalent bonds, van der Waals bonds, hydrogen bonds. I remember this from the 7-minute summary. And boom, this is an interesting equation, which I have seen in the equation sheet. So we're going to spend some time on it. The allowed values of the rotational energy of a diatomic molecule are E rotational equals EJ. I don't know, different subscript here, different way of calling the energy. Either the energy is E subscript J or rotational energy. They tell you this is the rotational energy. And they tell you H bar squared. H bar is literally Planck's constant divided by 2 pi. So in the equation sheet, they give you Planck's constant. Right? Planck's constant is right here, but they don't give you H bar, which is this right here. This is actually the equation we're looking at right now. H bar is called the reduced Planck constant. It's literally the Planck constant here divided by 2 pi. So the reduced Planck constant, H bar, and regular Planck constant, H, have the same units, but a different value. H bar is reduced by a certain amount, specifically divided by 2 pi. So keep that in mind, because if you don't know that, and it's not given to you in the equation sheet, you might fumble a little bit over here. So anyway, this is the equation. Let's take a look at it. We have some J's over here. We got an I, we got an H bar. Plug in all this stuff, it spits out an energy. What is the energy? Rotational energy. Rotational energy of what? A diatomic molecule. J can be 0, 1, 2, 3, whatever. I is the moment of inertia of the molecule, and J is the integer called the rotational quantum number. So J is very similar to N, except when N was talking about those shells that the electron can exist in around the nucleus, J is a different quantum number. It is a rotational quantum number. So a diatomic molecule, you can imagine like a carbon atom bonded to a carbon atom, diatomic, or maybe like hydrogen bonded with oxygen, I don't know. They can rotate like this, right? So I guess they can only rotate in specific like locked quantum states, right? Just like how the electron can exist in only specific shells. This is the exact same thing. You plug in this J is an integer, you plug in 0 right here, 0 plus 1 gives you 1, 0 here gives you 0, so the J equals 0 gives you 0 rotational energy. You plug in 1, 1 plus 1 equals 2, 1 over here, so 2 cancels with this 2. H bar divided by I gives you the rotational energy of the J equals 1 quantum number. The selection rule for transition between rotational states is this. I haven't seen this too much, the selection rule. Maybe you can ask ChatGPT what is selection rules in rotational energy, rotational quantum number. Not too sure. Anyway, I'm just showing you this equation here. One thing I want to note though is I is moment of inertia. This is not given to you anywhere in the equation sheet. H bar is not given to you, and I is not given to you. So keep this in mind. If you have a problem related to this and you don't know what I is or how to calculate it, you're screwed because you don't have the equation. So let me just check over here quickly if they have I, and they don't. So I'm gonna just go here. So here's what we're looking at. Rotational motion of molecules. E rotation, I guess they talk about like a section 21. This is the classical mechanics. They introduced this. Moment of inertia for a diatomic molecule. This equation is not given in the equation sheet, so make sure to note this down. How do you find I? You have to know the mass of one atom in this diatomic molecule, the mass of the other one. You multiply the masses together, then you add the masses, and then you take the division like this. Once you have that division, you divide by r squared. What is r squared? The separation distance of those molecules, of those atoms in this diatomic molecule, which should be given to you. They simplify this whole equation by mu. Mu over here is called the reduced mass, which is everything here you see in the brackets. So keep this in mind, because if you don't know this, you will not be able to use this equation over here. And again, take a look at this. This is how they kind of discuss it here. They kind of talk about it like these little energy levels, like we saw with the N quantum number. They talk about the reduced mass. Here it is, reduced mass of a diatomic molecule. They kind of derive the equation a little bit, boom, 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 and then here's the equation as we see it in the equation sheet. Except they don't tell you that J can be 0, 1, 2. They don't tell you that this is rotational. They just tell you E is equal to boom. So this is rotational energy of a diatomic molecule. Make sure you know what I is. Make sure you know what H bar squared is, and you should be chilling. But if you're not chilling, you don't feel like you're chilling, rotation of a CO molecule, the J equals 0 to J equals 1 rotational transition of CO, which is carbon bonded with oxygen, molecule occurs at a frequency of blank. Use this information to calculate the moment of inertia. So here you go, you do it here, calculate the bond length, and then maybe there's some other examples here that they can give you. Vibration of CO molecule, I'm not sure. Actually, this equation I don't think they give to you. This equation I haven't seen in the equation sheet. Oh, never mind, here it is. So we can actually slam this equation as well. Let's take a look at this very quickly. Allowed values of vibrational energy. E subscript VIB, VIB, vibration, equals V. What is V? I'm not too sure. And they don't give it in the equation sheet, so we actually have to check. Aha. Here it is. They introduced the equation here, equation 43.9. V is an integer called the vibrational quantum number. Another quantum number. You plug this in, V can be 0, 1, 2. You plug in 0. 0 plus 1/2 is 1/2. 1/2 times HF. You have H, you have F. Maybe you can find F. And then you find the vibrational energy of that thing. Here, allowed values of vibrational energy. So I guess they manipulate this equation a little bit more, but we still have this V, which is the quantum number. We have this 1/2. H over 2 pi is the reduced Planck constant. So they don't simplify it here as H bar, but you can replace this with H bar if you want, or you can do, actually in this equation they don't replace it with H bar either, but H over 2 pi is H bar. They don't give this to you anywhere in the equation sheet. Then you have this square root K over mu. I think mu still here is the reduced mass. So anyway, take a look at this equation. They again give you a problem that you can do. Try out this problem. You can see the problem here. You can get some answers and you can kind of work through this. And there's some more problems at the back of the book. So very interesting. So we still haven't gotten to these two equations. I guess I started with these and these are going to be all the way at the end. But we covered this one here. Vibrational quantum number V gives you the vibrational energy of some diatomic molecule. Here you have K, which I think is spring constant or something like this. Mu, maybe reduced mass. Again, reduced mass is not given to you. Over here, moment of inertia is not given to you. So keep in mind these equations here might be given to you and they might throw you off since not all the information is in the equation sheet. This is why it's important studying with the equation sheet, because if you just look at this equation, you're like, yeah, I've seen this, I know what it's doing, and you don't know what I is, you are going to be screwed. So yeah, try a problem with this, try a problem with this, and let's take a look again at the summary of this chapter to see how we're feeling. So I read a bit of that, I saw this, haven't seen this before. Free electron theory of metals. I don't think this is on the equation sheet. No need to worry about it. We're going to keep zooming so I can find these equations finally with the 931, 931. Nuclear structure, chapter 44. Let's read the summary of this very quickly. Magnetic moment of a nucleus is measured in terms of a nuclear magneton. So they give you mu here, which is not the same as reduced mass. This is a different chapter, different thing. Okay, this looks familiar right over here. So I'm gonna stop real quick, take a look at this. E subscript B, binding energy. The difference between the sum of masses of a group of separate nucleons and the mass of a compound nucleus containing less nucleons, when multiplied by c squared, gives the binding energy of the nucleus. The binding energy of a nucleus can be calculated in mega electron volts using the expression boom. And then here we have a bunch of weird stuff, Z, M, H, N, M, N, M, and then this kind of double symbol. It looks like kind of elemental periodic table stuff. And then this 931, and you can round this 931.494 to 5. 931.5 mega electron volts U. Right here, we see the same thing. 931.5 in mega electron volts divided by U. 931.5 in mega electron volts per U. So both these equations, I know they're in this section here, nuclear structure, because I can see pretty much the exact same form of the equation here. I have a number, mega electron volts divided by U. I have some EB, right? One of the equations here, EB, is this one. So this actually looks exactly like it. We have ZMP. This looks a little different. ZMH here. Here we have plus N, little m subscript N. Here, plus N, little m subscript N. It's a little bit hard to see here, but it looks pretty much the same. And then we have minus, and another thing that looks a little bit different. Here we have M, and then all this elemental stuff, which they actually talk about it over here. We're going to see that in a second. But let's take a look at our version. Little m subscript A. So they replace this whole thing with little m subscript A. Let's take a look at what this is. MH, which is this thing here, MH, is the atomic mass of the neutral hydrogen atom. M with all this elemental stuff all the way at the end, which in our equation sheet looks like a little m subscript A, represents the atomic mass of an atom of isotope X, A at the top, Z at the bottom, and M subscript N is the mass of the neutron. So honestly, if you're confused by this, copy paste this whole thing into ChatGPT and be like, please explain this to me. But if you're curious, you can go see equation 44.2, which I will do in a second, and try to figure out how they derive this and how you can look at this equation and remind yourself what kind of problems do they do with this. Also, this Q equation looks super similar, but we haven't seen it yet. So what I want to do is check out what this equation 44.2 is. And I'm just going to go here to the beginning of the chapter and just sweep through it slowly. And actually, you can see here, they tell you Z, they tell you A equals a bunch of important stuff right here in this thing. And you can see here, iron, they have Fe 5626. So this little method of writing elements where this X, actually they show it right here, X with the A at the top and the Z at the bottom. X represents the chemical symbol of the element. For example, iron 5626 has mass number 56. Mass number is over here, A, right? That's the A right over here at the top, 56. And atomic number 26. Atomic number is this Z. And they tell you mass number is equal to atomic number plus N, which is the neutron number. So this stuff here is not given to you in the equation sheet, but you can see it's used somehow a little bit. So take a look at this, see if you can kind of remind yourself what this stuff is saying, and see if you can remember it specifically with the equation sheet. Like use the equation sheet to kind of string you along. Anyway, there's some examples here you could do. I'm just going to sweep forward and try to see if we have those two equations that I'm curious in. Here it is. Binding energy. And they write it again in a slightly different way. So this way of writing it is not the same as this way. So try to remind yourself this way here, what all these little symbols mean, and try to relate it to this equation here. You can also read nuclear binding energy. Here they do a full introduction of it. Here they do a full introduction, little pitfall. They show you a little graph that might be helpful. Boom, and it looks like this section doesn't have an example, which is kind of unfortunate, but we're going to keep zooming through and see if we can find that other equation. E subscript B, we saw in the previous thing over here, E subscript B was binding energy, and this is one specific form of the equation. Over here, we have again binding energy. This looks a little bit more complicated. This says this equation often referred to as the semi-empirical binding energy formula. This does not appear in the equation sheet, so I don't know if you have to study it. No need to stress about it, but if you want to do an example, here it is. Let's zoom through a little bit more. Interesting. Okay, we're getting to some other equations that I've seen. These equations actually, this one, and this one, notice them, n is equal to n subscript 0 with this little e to the power of minus lambda t. They actually graph it over here. You can see this little decaying function. I always remember this e to the power of negative t is a decaying parameter. And here they have t is equal to 1/2, 2t 1/2, some stuff related to half-life. Actually, they give you the half-life equation over here. T subscript 1/2 is half-life. And they tell you you can find half-life if you have lambda and you have this number here, 0.693 or ln2. So this equation is in the equation sheet. And this over here, exponential behavior of the decay rate. This equation, which is related to this one, n subscript 0, you can see the n subscript 0 appears here. And actually, the derivative of this equation with respect to time gives you this equation. So you can see that here. Exponential behavior of the number of undecayed nuclei, exponential behavior of the decay rate. 1, 2, 3 equations. You can see those right here. So here we have the half-life equation, boom. Here we have the decay rate equation. Not sure the difference between this one and this one, but here you have all those 3 equations. So take a look at some examples. They do examples here. They have a pitfall prevention. They talk about some things. 1 Curie is equal to 10 to the 10 decays. This is also given to you in the equation sheet. It is right here. 1 Ci is equal to 3.7 times 10 to the 10 decays. 3.7 times 10 to the 10 decays, right here. So you can kind of tell this is a little bit important in this little Becquerel unit, which is equal to 1 decay per second. How many nuclei are left? This is a problem that uses this equation here, which you guys saw at the top of the equation sheet right here. So definitely important to do these problems here, these examples. Let's zoom through again to see if I can find that equation with the Q. Finally, here we go. And I think this is literally the final equation sheet, or the final equation in the equation sheet. Here is what we're looking for. What does this mean? Do we have a name for this? The energy Q is in joules when the masses are in kilograms and C is the speed of light. When the masses are expressed in atomic units, U, however, Q can be calculated in mega electron volts using the expression boom. So here we go. Q is equal to capital M subscript capital X minus capital M subscript capital Y minus capital M subscript alpha times 931.5 mega electron volts divided by U. Remember, U is actually a unit conversion between kilograms. And here they're telling you, if you use this equation and you use the speed of light, C, and you use kilograms, then this equation here is in joules. But if you're fancy and you want to use atomic mass units, U, then you can express this equation in mega electron volts. So one way of doing it with mega electron volts, one way of doing it with joules. You don't need to worry about that. This equation here is given to you in mega electron volts. But if you want to convert between electron volts and joules, here's the equation to do that. Joules, electron volts, you could use this over here to convert between those two. And this equation is actually the disintegration energy Q of the system. So there's a pitfall prevention here. Another Q we have seen is the brand new meaning of this. Okay, so you could take a look at this pitfall prevention. This graph might be important here. This little table of a bunch of values. You don't have to remember all of this. This is going to be given to you. Mass of neutral atom in units of atomic mass, this U. Maybe you can pick out like lead. You're doing a problem with lead. They're going to give you this number. You can plug it in and calculate some disintegration energy. The energy liberated when radium decays. Radium nucleus undergoes alpha decay according to equation this, 44.12. Is that the one that we are taking a look at here? 44.12. No, it's actually this equation here. So this equation is something completely different. Alpha decay. They give you an element, it decays, it spits out an alpha particle, which looks like it's just helium. And they use the Q equation, which is in the equation sheet, to find the, what are they asking us? Calculate Q for this process. They literally say calculate Q, but they could replace this Q with disintegration energy. If you didn't know that Q means disintegration energy, you're screwed. So it's good to do this problem, try it out. And that basically covers, I think, all the equations here. We did this one here, Q, disintegration energy. We did this one here, their binding energy. These two are kind of like complementary equations. We kind of took a look at the Heisenberg uncertainty principle. This is in the first quantum physics, quantum mechanics chapters. We looked at a lot of the quantum mechanics, quantum physics kind of equations with all of the quantum numbers. So we have the n quantum number. Here we have the vibrational quantum number V. Over here we have another n quantum number, another n quantum number, transitions. Here we have the rotational quantum number J. And I guess since I'm not sure if I've covered everything, we're going to go through everything very quickly, one by one, all of the equations. Boltzmann constant, Kb. I have not seen this used. If you see K subscript B, you can plug it in and solve. Coulomb's constant, K subscript E, you could see that in a couple of equations here. I've talked about it. You could plug that in and use it if you want. Rydberg's constant, related to this equation, but not directly used in this equation. This equation is manipulated slightly to get an equation for lambda, and then it is simplified and they plug in the Rydberg constant. Boom. Femtometers to meters conversion, cool. Curie to decays per second, cool. Mass of a neutron in kilograms, Planck's constant. Remember Planck's reduced constant, which is h divided by 2 pi, which is h bar, which appears right here, not shown. So remember, you have to remember this. ME, mass of the electron in kilograms, cool. Speed of light in meters per second, dope. Proton mass in kilograms, astounding. Permittivity of free space. This is a constant that is normally coupled with this Coulomb constant. You sometimes see this in ENM. Not too useful. I haven't seen it appeared in any equations. It's not anywhere in any of these equations, not that I've seen. But if you need it, here it is in its value and all of its units. Remember, units help you out a lot. An equation has to have the left side and the right side match the units. So you can use that to kind of help you out, make sure everything looks good. This now we found out was disintegration energy. It is in the atomic section. Take a look at some examples. Mega electron volts per U, which is the atomic mass units. Awesome. All of these things here, I didn't actually see what they were, but you guys can do those problems. You now know which section of the book it is. You also know disintegration energy. So you can check ChatGPT. I have a disintegration energy equation, which is Q is equal to mx minus my minus m alpha times 931.5 mega electron volts per U. I want to do some problems with this. Please help me learn it. What is it talking about? What are all these m's in here? Why are we subtracting them? Why is this 931.5 here? Please explain this to me. You're gonna be chilling. Just make sure to ask the right questions. Lorentz transformation equations. I haven't done a problem related to this. I also haven't talked about them too much, but take a look at this and try to ask yourself, why is it that y prime is equal to y, z prime is equal to z? These two are the same, like they don't change, but x is not equal to x prime. There's some difference happening here. So you have x, y, z, 3 dimensions of space, 1 dimension of time. Why is the time equation also looking a little different? Try to ask yourself that. Do a couple problems related to this. Chapter 39, the relativity section. Zoom up over here, electron volts to joules. Over here you have mega electron volts. Also keep in mind, mega is normally times 10 to the 6. It's like 1 million electron volts. So if you want to convert between electron volts and joules, you could use this here. Charge of the electron in units of coulombs. Remember, electron has a negative charge. So you could use this if you wish. Wien's law, I did a problem on Wien's law. This is the only equation that is talking about the black body radiation phenomenon, which is in the first chapter of the quantum physics section. So take a look at this. The quantum physics section has black body radiation, photoelectric effect, Compton effect, which I have not looked at actually. I'm just going to talk about Compton effect very briefly here. And I think that is all the stuff in the quantum physics section. Some more stuff as well, but anyway, take a look at that. Try to do a problem related to this. Atomic mass conversion to kilograms. If you want to convert the mass of the neutron from kilograms to atomic mass units, you can use this equation here, you can use this equation here, cancel some units out, multiply some things together, convert. If you have problems converting with that, leave a comment. I can maybe do a quick video. There's a lot of conversion equations here. Curie to decay rate, electron volts to joules, atomic mass units to kilograms, pounds to kilograms, Fahrenheit to Celsius. You have to know how to convert between these two if the question is asking you, or if you kind of get stuck somewhere and you need to cancel some units out. This equation is very, very commonly seen. You may have seen it in the optics section. Speed of light is equal to the wavelength of the light times the frequency of the light. Make sure the units cancel as well and everything looks good. You have the speed of light over here. De Broglie wavelength. Lambda is equal to Planck's constant divided by momentum. This here is one of the only equations talking about wave-particle duality. Normally, particles have momentum p and waves have wavelength, but this equation, the de Broglie wavelength, connects both of them through the Planck constant. So take a look at this. If you have wavelength and you have Planck's constant, which is actually given to you right here, you can find momentum and vice versa. Energy of a quantum mechanical system which rotates. Rotational quantum numbers J can be 0, 1, 2, 3, whatever. Moment of inertia is not on the equation sheet, so make sure you note this in your head. What is moment of inertia? Do 2 problems related to it. Write down what is moment of inertia on your hand, on a piece of paper. Keep it in your pocket. Try to remember what it is for the final exam. And then when you enter the final exam, just write it down on the top of the piece of paper. This is moment of inertia, so you don't forget it. Then we have gamma factor. Take a look at gamma factor, what the graph looks like. This gamma appears everywhere. It appears right here in the Lorentz transformation equations. It appears, it doesn't really appear here. It appears over here. Any kind of relativistic thing, you will see this gamma factor. So try to understand it. What is it doing? Why is it in the relativity section at all? Relativistic energy, take a look at this. Maybe there's some problems that you can do here related to this, but I think here they may just ask you, what is the relativistic energy of a thing going with a specific momentum with a specific mass? Plug those numbers in, boom, you get a relativistic energy. This equation here is really going to mess you up, so please do a few problems related to this. I showed you earlier in the video. Do some problems related to the Lorentz velocity transformation equation. ChatGPT, what is the Lorentz velocity transformation equation? Show me a few examples. I need to practice for the midterm or for the final. Please show me an example. You can couple this with the Lorentz position and time transformation equations. This is a fantastic little study session. These 2 equations here. So make sure you study those. This equation we just saw recently is the binding energy of some kind of like elemental composition. Again, I didn't really talk about all these symbols here, but you can see it's very similar to the disintegration energy equation. So do a problem related to this, see how these equations are used. Try to explain to yourself what these symbols mean, because again, they are not exactly the same as the ones in the book. They mean the same thing, but they look a little different. So try to explain that to yourself. Heisenberg uncertainty principle. All I'll say about this is, if you're really certain about the location of the particle, then you're uncertain about its momentum. So if you zoom in and you know, like, oh, this particle is right here, you don't know how fast it's going. But if you know how fast it's going, you don't know where it is. This is kind of related to waves. I don't know, if you zoom in and look and say, like, the wave is right there, you don't know how fast the wave is going. But if you zoom out and look at how fast the wave is going, you don't really know where the wave is. I don't know if that makes too much sense. Take a look at some problems done with this. Most of the time, how I've seen it is just, they ask you, if we know the uncertainty of the particle's position, then what is the uncertainty in the particle's momentum? You use this equation here. It's an inequality, and you have Planck's constant, the reduced Planck constant, h bar, which again is Planck's constant divided by 2 pi. That is divided by 2, and then you have this equation here, which you can kind of manipulate. I actually wrote over here, h bar is equal to h over 2 pi. Very important to remember, not on the equation sheet, so write that down. Over here, we have energy of an electron in a specific energy state. 2 different ways of writing the equation, one with electron volts, 13.6, one with this entire constant over here. Again, all these constants are given to you. A naught is over here, electron charge is up there, Coulomb constant is the thing up there. Plug all those in, you get 13.6 electron volts. Make sure the units cancel properly, you should be chilling. And they tell you here n is equal to 1, 2, 3, 4. Quantum numbers are super important. Make sure you know which ones can plug in 0 and which ones can plug in 1, 2, 3. The n, you cannot plug 0 in here. You plug 0 in here, you divide by 0, you're screwed. You get some error. So that is what that is there. We're going to move on to the last thing over here. Relativistic momentum. Again, I'm not too sure what example they might give you here. It's like, an object is going with a specific velocity, find its relativistic momentum. Since gamma is included here, you need to plug in the gamma factor here, which includes the velocity of the thing in here. So the momentum changes. Momentum can be plugged into energy right over here, and you get relativistic energy. Plug in relativistic momentum into here, you get relativistic energy. That gives you this over here, relativistic energy. And here you get relativistic kinetic energy, which is the relativistic energy, gamma mc squared, which is given to you here, minus the rest energy, which is mc squared. Here we have the frequency of a photon emitted when an electron transitions from an initial energy, an initial n quantum state, so maybe this one here, it transitions down. The only way it can transition down is if it loses energy. How does it lose that energy? It emits a photon. What does the photon's energy look like? The photon's energy has this frequency. You can find the energy of the photon by multiplying the frequency by Planck's constant. This is also an equation not given to you, but you can use the photoelectric effect equation as a little cheat. Kinetic energy is the same units as energy. It's just kinetic energy here in the photoelectric effect, they subtract this phi, which is the work function. But if you just want to find energy, you could just do h times f. If you want to convert between f and lambda, you can use this equation here, which is speed of light equals lambda times f. So this gives you the frequency of an electron transitioning between these two. If you want to excite an electron from a lower energy state to a higher energy state, you have to shoot it and give it energy with a photon. How much energy does the photon need? It needs a specific energy in terms of frequency, which you can get using this equation here. Relativistic energy, we already spoke about that. Photoelectric effect is pretty much the same thing as this equation here. You have a piece of metal, you're shooting it with light. Light has energy. The energy comes from the frequency of the photon, not the intensity. So the way I think about it is frequency is the energy of the photon. If you shorten the frequency, if you shorten the wavelength or increase the frequency, you get really strong photons like gamma rays. I always imagine like gamma is high energy because I think of the Hulk. The Hulk transformed into the Hulk because he was blasted with high energy radiation, which is gamma. Gamma has short wavelength, high frequency. You don't need to remember that. Anywho, in order to liberate an electron from a metal with a specific work function, phi, normally the work function is going to be given to you, but sometimes they're going to give you some other information and say, hey, we shoot this metal with a frequency x, and electrons with a specific kinetic energy y come out of it. Please find the work function of this metal. So the photoelectric effect, take a look at chapter 40 for problems related to that. This equation here, energy of a electron that is chilling in one of these energy levels. The first energy level is the ground state, that is the lowest possible energy. You plug 1 over here, you solve this, you actually get 13.6 electron volts. So that is the energy of the electron when it's chilling closest to the nucleus. Same kind of equation as this over here, same kind of equation as this over here. Decay rate parameter. I'm not sure what this is, you're going to have to take a look at this, but basically you have some decay related to time. I don't know, you're going to have to do some problems related to this. I'm just showing you the equation here. Half-life, also related to radiation and decay. Take a look at this, take a look at this, take a look at this. All these three, take a look at chapter 44 or whatever it was over there. Do some problems related to this. I'm not sure what else to say about this one. Here we have energy of vibrational, vibrational quantum energy of a diatomic molecule. So you have two atoms, they're vibrating, and the vibrational quantum number V over here could be 0, 1, 2, 3. I think it could be 0. It could just be 1, 2, 3. I may have forgotten. So try to keep those things in mind as well. Here you have Planck's constant 2 pi. Here you have, I think, a spring constant and the reduced mass. Plug those numbers in, boom, it spits out a vibrational energy. And then again, we have the Heisenberg uncertainty principle for energy and time. Super high uncertainty in the energy means that you're pretty sure about how long the process is taking. Kind of the same thing as position and momentum uncertainty. Again, check ChatGPT, position momentum uncertainty relationship versus energy time uncertainty relationship. Give me some problems, help me practice for a final exam. And then we finally have the last constant here, which is A naught, which I think is the distance between an electron and the hydrogen nucleus. So I know this was a bit of a jumbled kind of introduction. I did not show you guys that much useful information. I kind of just wanted to talk about each of these equations so that once you have the time, and if you feel uncomfortable, like let's say this equation here, this half-life equation, I have no idea what this is doing. I'm gonna hop in, try to do a couple problems. I'm gonna release a video shortly after this one that shows you guys what you can do to study for this exam. So take a look at this. Try to study each day just a little bit, as much as you can, but try to do at least like 10 minutes, 30 minutes, something like this. Thank you guys for watching. Please let me know in the comments down below if you have any questions, if anything here is confusing to you. I know it looks crazy, but try to break it down. As you can see, I try to break it down in a couple colors. I used pink and red and they kind of merged together. Maybe it's not the best kind of choice, but you have basically 3 things to learn: relativity, quantum physics, atomic physics. That's it. It sounds like a lot. It is a lot. It's a lot of shit over here. It's even more shit because you don't have everything in the equation sheet. So keep watching, keep learning, keep trying to remind yourself, do some cue cards, and take a look at my other video, which I'll post soon, which will be how to study, or at least my strategies on how to study. Thank you for watching. Peace.